Greetings, I'm Katarzyna Balcerak Kobos, and I would like to walk you through my presentation, Necessary Brain Subcomplexity. The itinerary is such. First, I will share some definitions with you, then discuss complex basics, basic caveats, and colorful corollaries. Let me say a few words by way of introduction. In my presentation, I argue that brain complexity is not a self-contained phenomenon, but relies on incompleteness by design to admit outside factors. Indeed, it might be geared towards forging the external quality of signals. Rather than emulate the rest of reality, it carries placeholders within its blueprint for the entire world it is supposed to represent. It allows these signals to be identified as stimuli. No amount of stimuli pounding on body will turn them into signals. It is the job of the brain to ensure it invokes the world at large. The only means available to it is complex network dynamics. But exactly how complex this machinery must be for the inner neurotransactions not to drown out all signals from the outside, not to become a world unto itself. Let me debunk one obvious misconception of my proposal. I'm not saying that complexity is just an artifact of the brain's history, a byproduct of the brain's long and adventurous evolution. It's too costly to be carried around for sentimental reasons, pun intended. Complexity is sure to be the cornerstone of cerebral proficiency and performance. But it's not the end of the story and needs to be framed within a broader context. But first things first. Some definitions. What is complexity? For the purpose of this talk, let's assume that complexity is a sufficiently dense and spacious network of interconnected elements, which is a very layperson way of saying that it evinces hierarchical modularity, with interactions within subsystems stronger than interactions among subsystems. And what is deemed conscious? Well, I'm not after the account of mathematical reasoning or any other higher cognitive functions. For me, any felt sensation is a case of consciousness at play. It might be tempting to consider complexity itself as robust enough to give rise to consciousness. While this may be the case, we must be open to the possibility that complexity may just be a prerequisite, a necessary but insufficient condition that merely sustains conscious phenomena. Conscious processes may only prove viable in the framework of complexity. It may be the case that consciousness requires a critical mass, that it is a stochastic phenomenon resulting from the joint activity of multiple elements, that is, neurons. For some level of randomness, the brain should not be a trap to keep all the neurons in check, but it should afford some degrees of freedom within the structure. Of brain. Already topologically unfeasible, a structure where every neuron would be directly tied to every other neuron would collapse into a flat array tantamount to an overgrown unicellular multinucleic neural mass, missing the target of constituting a higher order integral structure. There would be no brain, rather a superneuron. This hypothetical borderline condition is called metal of brain in literature, and refers to the scenario when 128 billion elements effectively form just a single element. Connectivity should come with a cadence. The connections should be parsed in order to retain any relevance to the whole. The kind and number of interfaces between neurons matter only if they are not the only ones possible. A brain with each neuron latched directly somehow to all the rest would be stimulus invariant. There would be no way to make a difference to its internal organization, as it would have already reached its upper limits of interconnectivity. One-on-one connections would render it indifferent. Had there been only one option to enact in respective scenarios, the brain would be a machine running on autopilot, with a repertoire of different sequences to go through in specific settings. Wiring seems to arise from selective connectivity, the bridges between individual neurons that are not established, the actual gaps that are not synaptic gaps, which indeed play the role of couplings, prove to be vital. They can stand as the backdrop. Function relies on a surplus of potential connections. Bear in mind, however, that this surplus is an intracerebral feature. This is just the universe, realm of all the connections possible at a specific time against which the actual networks or pathways may be plotted against. It constitutes a virtual space within which all individual neural connections can play out. So far, the network architecture is considered to be agnostic of the world at large. Parsing accounts for the viability of the array itself. It does not secure, validate, or have any other role in the alignment of the brain with the outside world. No inner workings would be different if the brain were self-confined without incoming or outgoing information. However, a robust theory of cerebral complexity has to incorporate external access points. Otherwise, the whole business of representing reality or tapping into it would be contingent at best, almost irrelevant for the makeup of the structure. In principle, we know how to embed brains inside the world. We devise theories explaining how on earth does it make sense to preserve and even develop further such a costly organ. On Earth, apparently, it does make sense, though, since we humans are around. We bring ice age, cooking, women's pelvis sizes, pension for coastlines, and wide vistas into the equation. Refer to Rack Sykes mentioned below. But how do we nest the world inside a brain? There's something about brains and central or decentralized, think octopi, nervous systems that can crack the world open. Something that can capitalize the obscure currencies of wavelengths, textures, volatile particles, and use them to get one's bearings. Not only to know of what's outside, but to know of one's own location and means of reacting within that outside context, so that it actually makes sense to be aware of oneself in the plot of things in order to follow a specific sequence of steps or take a particular avenue of action. Jung highlights, for example, that evolution-wise, consciousness accompanies sensory inputs that are actionable. Regardless of how fascinating it is to seek out the origins of vision, echolocation, and the like, we should be interested not just in receptors as add-ons to brain structure, but the very characteristics of brain structure that betray this about the world. Is this even the case? Words have meaning only for us, otherwise conceived of, they are just scribbles on paper or screen, or sequences of sounds. But is there something about the brain as the whole, neural circuits, or the very shape or function of neurons, or their connections, that is telling? In other words, if the brain is about the world, does this come about via mapping, a particular setup originating under specific circumstances? And on what grounds does a set of dependencies qualify as a mapping? On most accounts, it does so by virtue of causal relations. It's the origin story that couples brain regions, neural cell types, and respective circuits to specific varieties of goings-on in the extracranial world. In fact, a whole network of origin stories that may play out on both philo and ontogenetic levels. If it is mapping that affords access to reality, neural structure proves not effective in its own right in providing a grip on the outside world. But it's plain to see that this proposal carries the risk of infinite regress. Mapping differs the problem of the adequacy of representation beyond anything neural and into the realm of extracranial reality. At least, neural structure is relieved of directly referring to the world, but nothing specific is posited as the driving force behind the transcranial alignment of reality and its representation. So, where should we start our quest to screen cerebral structure for sign of its involvement with the world? The obvious departure point are the connections themselves. What are these? These could be receptor binding sites. Okay, wireless signaling. But here, the connection does not really come online. It's not actuated. The connection only occurs via message dispatch. It's not a binary affair. A specific molecule may be released into the extracellular medium and then captured by a receptor on a neuron. No intimacy here. More promise is carried by wired connections. These are more effective and spatially directed. It could be electric gap junctions or, last but not least, chemical synapses. But how are these interconnections formed? Apart from hardwired circuits, it is common knowledge that the neurons that fire together wire together, as the so-called Hebbian rule goes. What is meant by together may not be genuine synchronicity, but rather firing within milliseconds apart from one another. The rule stipulates, and is well substantiated by the actual findings, that what may be initially a coincidence becomes the principle. It is correlation elevated to the status of causality. Of note may be the fact that not all stimuli actually stimulate receptors. Some rely on a reverse rule of action. The same may be said about intracerebral connections. Some actually turn off downstream neurons. So let's revisit some common misconceptions. It should be borne in mind that not all stimuli activate receptors. Some deactivate them, as may be seen in visual receptors in the cones. The receptor maintains activity that is actually disrupted with an incoming photon. This showcases the role of endogenous activity in neurons. Not least in the lineup of intraneural links are the GABA operating inhibitory neurons, balancing out excess excitatory spikes. Without them, the brain would crash in a sequence of paroxysms, with spikes generated in feedback loops. Humphreys says, for example, the cortex is set up so that the total amount of inhibition is just right to cancel out the total amount of excitation. And Burgoyne says networks made of purely excitatory neurons, or of neurons not respecting Dale's principle, are unable to form or to maintain the modular architecture induced by the stimuli, where Dale's principle is understood as the distinction between excitatory and inhibitory neurons, and is crucial for the consolidation of stimulus-driven neural assemblies. Brain requires the differentiation into excitatory and inhibitory neurons to represent the world, to emulate the arrangement of the environment, to incorporate the incoming signals as stimuli. But this dichotomy is a feature of neural structure and has nothing to do with the outside world. There is a number of caveats that may arise in connection with accentuating the structural characteristics of the brain. I will try to recount the most prominent ones. Before we give too much credit to this relational makeup of neural mass, let's consider the ontological arc of every human and most other sexually reproducing life forms. Connections in the brain perish at death. They are not transferred. Although relaying is their superpower, they are not part of the relay race between generations. The entire organism is reset to a single cell, a zygote. Connections are regrown, not inherited. They have to be refashioned upon individual development. In the same vein, let's attend to the types of connections for a moment. As Michael Levin advocates, gap junctions that predate chemical synapses in ontological development, and definitely in the story of evolution, bear no information on the origin of the electric potential propagation. Whenever the ions flow from one neural cell to another, it is as if the signal was implanted into another neuron. The cell treats it as arising within itself, not coming from the outside. This is a case in point that neural signals are not readily traceable to external stimuli. The structure of wiring proves of greater importance than its mere continuity. Levin speaks of gap junctions as erasing ownership metadata information on action potentials. In the face of such an argument, these are more fusions than connections. Why do we value relations over matter? What is the rationale behind this mundane transcendence? For one, the very location of the brain within the vault of the skull primes it for transcendence. Transcendence of its physical setup, that is. The neural suite, with its glial assistance stuff, action potential, synapses, and neurotransmitter surges, prove to be but scaffoldings for something that steals the show, complexity. Once that kicks in, the physical technicalities no longer matter. Only structure does, or so it seems. As neurons are mainly in the business of handling signals, both originating and headed externally, wherein they form larger circuits by the sheer act of signal relaying, they are designed to transcend their material constraints for the sake of purely relational dependencies. This setup seems to give ground to functionalism, a stance according to which mental states are material invariant and it's what they do that counts rather than what they are made of. Since we're not in a position to provide a detailed account of neural architecture, we're prone to acknowledging it as the breeding ground of all mental functions. In fact, however, we don't even know where the effect of the material makeup of neurons and functional ones begin to show. Since the brain is so packed with connections, there's no need to seek beyond it for consciousness. But admitting so much does not settle at what scale exactly occur the very processes that underlie neurons' ability to sustain consciousness. It leaves open the question as to whether it is something inside the neurons that does the trick, or maybe it is engendered by the very setup of neurons. If complexity is vested with the powers to carry consciousness, one may rest on the fence as to whether consciousness arises as a function of distributive characteristics of neurons, their internal makeup, or, on the contrary, their collective arrangement. In the former case, consciousness is seen as rooted in the technicalities, in the antics, foibles of neurons, as an evolutionary product in all its randomness. In the latter case, functionalism is implied, with neurons contingent on the structural aspects. They may be only one possible rendition of consciousness and could be replaced with a different type of material. Maybe we should be looking exactly for something unseverable, something that cannot be disentangled from its medium. More than that, maybe it's not an all-or-nothing kind of challenge, and various cognitive features and processes evince a varying degree of reliability on their material substrate, to the effect that some cognitive features are medium-dependent, whereas others can be readily isolated and transferred. Computation is an obvious candidate. Much as connectivity seems to be a distinct feature of brain tissue, not all possible connections are made. Connections are selected. For there to be varieties and hierarchies of neurons, division into 6 neocortical layers, identification of distinct subsystems relying on respective neurotransmitters, neurons cannot exploit all possible connections. Many are not made at all, many are undone. Early onset neural pruning and tuning is a case in point. Neurons do not handle various bodily functions, sensations, and cognitive tasks by virtue of being different from other neurons. There are no heart-tending neurons that would be distinct in type, although there is indeed a great variation between them. Rather than proceed through direct diversification, they form a multiple-scale architecture whose inner workings allow for freedom of behavior and division of labor. They never reach a one-on-one super-dense interconnection threshold. They are not ultimately fixed in their firing pattern and enjoy room for a varied response. It's best to make 2 disclaimers here to disperse any doubts that might arise. By positing that the brain cannot reap the benefits of all the staggering possible connections between its components, I do not endorse that it fails to tap into its full computation power and consistently delivers below its competence, along the lines of catchy slogans that we're only using 10% of our brains. My thesis rests on the assumption that cerebral networks should not be choke-full of all and any feasible interrelations. Rather, they should be sparser than functional constraints allow. It is also no intention of mine to deny the brain a robust architecture designed to maintain fail-safe function under challenging conditions. Surplus is definitely built into the structure to secure proper functioning in case of mishaps. As all computation hardware, brains rely on redundancy for resilience. This redundancy is not scaled down to circuits charged with extra tasks to take over a failed operation, nor is it about plasticity that enables the brain to reconfigure its workings to adjust in the wake of damage to neural tissue. Surplus is also exemplified in the availability of multiple sensory channels to fetch and double-check vital stimuli. See Young, for example, mentioned below. Several senses guide decisions that are essential to animals, for example, foraging for food. Nature is no fool, and even the tiniest creatures come equipped with several access ports to outside reality. The pursuit of the workings of consciousness has led many to trace it back to spontaneous neural firings, otherwise not related to any response to stimuli. Isolated neural events, seemingly unbidden and coming from nowhere. Virtual islands within the brain. Mike Humphries, for instance, has an entire chapter entitled "The World is Not Enough." Therein he says many spikes, possibly most spikes, have no cause in the outside world. Whole network of cortical regions are paradoxically at their most active when you're quietly resting, eyes closed. When you do something, this network reduces its activity. The spontaneous activity in this default network is not only no echo of the outside world, but is also reduced by engaging with it. And he goes on to offer the observation that there are spikes in the retina and the visual cortex before the eyes open. Endogenous fluctuations are credited with sustaining brain function. This ongoing rehearsal of functional couplings may be a requirement for the continued maintenance of the cognitive architecture, or it may serve to prepare the brain for adaptive responses to intermittent environmental stimuli by continually replaying the past or imagining the future. That's sports. Spontaneous spikes are the brain's solution to the deep problem of survival. The body doesn't have to wait for them to be created, as they are already there. That's Humphries. The significance of this role is corroborated by the volume of energy the organism is happy to expend on it. For example, Reichel and Minton point out that evoked activity constitutes as little as a few percent, with the prevalence of spontaneous activity. Since the brain first needs to develop to capture incoming signals, let alone interpret them, it must be primed to do so via endogenous activity, when not coupled to outside stimuli. This seems to be of vital importance in ontogenesis, with fetus growth relying on such mechanism, but also in the adult brain for maintaining functional homeostasis. The initial connections between neurons in the cortex seem to be made at random, synapses appearing wherever axon touches dendrite. How far a neuron extends its dendrite as it develops is not fixed, but is regulated by its own activity. The tree grows if the neuron is not active enough, seeking new inputs, a bigger legion to drive the neuron to its tipping point more easily. And that's Humphries. In this talk, I explore if there is something about the very makeup of the complexity that flavors the workings of neurons as being of the outside world. And indeed, there are traces to pick up. On this account, representation is an activity. Representation is not just a response to external stimuli. It is an active pursuit to encounter what's beyond, regardless of whether there is a fresh portion of inputs. As I hope to have demonstrated, it stands to reason that to entertain the possibility that there is something identifiable in the cerebral architecture that makes it what it is. That the structure's affiliation with the world may be identified as not one of sheer correlation, but of projection, even inclusion. For the purpose of this talk, however, I forgo discussing whether sensory experiences are models or predictions, which I think they are. There must be a feature that predisposes the brain to play such a role. While brain mechanisms must be ultimately informed by the phenomena in the extracranial reality in order to bear affinity to them, the very fact that they refer to the outside world must not be derived from the outside world. It is to be devised internally. Some UA is important for turning the tide inside the brain with focus on predicting rather than representing the environment. In this view, spontaneous spikes are there to assist spikes evoked by the outside world. Spontaneous spikes are already carrying most of the information the brain needs to act. They are prediction. That's Humphries. But if the spontaneous spikes of neurons in your cortex really are predicting the world, then no matter how they are doing it, a simple fact should hold true. The spontaneous activity from neurons will consistently look like activity evoked by something happening in the outside world. And that's Humphries again. The target structure seems to include the hiatuses and clearances between the neurons as much as the neural cells themselves. any pattern connectivity requires the identification of primary building blocks. Individual neurons must be first disarticulated in order to reconnect by way of synaptic discharges and action potentials. And this statement does not merely stipulate the obvious, that it is a prerequisite for any composite entity to have distinct constituents. Thus construed, however, there would be no difference in type between a set and an organically interconnected whole, an organism. A complexity stands out by not having its units defined beforehand, but by taking on the job of identifying its own units. This happens through balancing order and disorder, that is randomness, offsetting segregation by integration. In a way, complexity is a consistently flawed order. Please refer to Sporns below as well for citations. The units must be discrete enough to accommodate unity of function. And since we're talking about complex systems, phase transitions constitute one such extraordinary example. Think of the incredible evolutions of a flight of starlings, or water freezing, thawing, or boiling. These dynamic systems are not a follow-up to a set of previously extant elements. They actively tease out their units. They are truly collective phenomena, where differentiation into components proceeds alongside and by virtue of the integration of their function, or vice versa. Segregation and integration in the dynamic patterns of functional and effective brain connectivity can be defined in terms of statistical dependencies between distinct neural units forming nodes in a network. That's Sporns. On my view, representation is not a supplement to outer reality. Cerebral architecture may not so much reflect the world, umwelt, environment as accommodated whole, implicated in the blank spaces. That is why it never reaches its maximum connection capacity, but still preserves a richness that can host most of its environment. There is some slack that allows for all the hierarchies to form. This is an interesting case, a structure of units that can best serve their function at a level inferior to their full-blown relation-forming potential, a complexity whose blank spaces are its legitimate components. Such a structure, in self-referential terms, is a subcomplexity by design. It's a trimmed variety of what could be a 128 billion combination of connections. The least that can be inferred is that here the entire logic of optimization is appended. The powerhouse of connectivity makes less of connections than it can, even culling some of them in the process, and is all the better off for it. A complex structure, such as a brain, maintains top outcome by keeping its feasible connections count below maximum. It over-delivers by underusing its potential. Brain's activity is ramped up by nil. It's either that, disorder, as Burns would have it, or a way to actually let the light in. The brain is surely a part of the universe, but here's a proposal of how the brain makes the universe a part of its own complexity. Thank you.